So, in view of many queries on simplified calculation of Bosch gas volume, this presentation is on the same purpose. So, calculating the Bosch gas volume in easiest and simplified approach is essential for all operators to know, especially what is going wrong or right or favorable, unfavorable in the lower regions. What are the lower pressure losses are there, and as they are very important because entire raceways area is come across this high pressure loss region, and hence it is essential to know our regulation and monitoring of Bosch gas volume also, so that we can able to know that whether the pressure losses has gone up due to higher Bosch gas keeping the same permeability, or we have a same Bosch gas but our permeability went down. So this evaluation helps operator to in understanding rhyme and reason and corrective action in operating day to day. So today's session will break down the calculation into clear steps, making it easy to replicate for plant operators or academic exercises. Our focus is how to determine the Bosch gas volume while neglecting hydrogen using typical plant data like hot blast volume and oxygen percentage. Now coming to our next slide, from where we shared most important data on oxygen volume in hot blast. So let's start with the oxygen in hot blast. Take the total hot blast volume, say 7500 meter cube STP per minute, and multiply it by the oxygen percentage. Here 27% we took. So 7500 meter cube per minute multiplied by 0.27, that is 2025 meter cube per minute. That gives around 2025 meter cube per minute of oxygen supplied. Now this oxygen volume is the basis for downstream gas calculation. Now coming to the nitrogen volume in the hot blast next. So we have to calculate the nitrogen volume in the hot blast using remaining percentage, that is 100 minus 27%, which gives you 73%. And so we can say that 7500 multiplied by 73% getting converted to 0.73, which gives 5475 meter cube per minute. So so our output is 5475 meter cube per minute. So nitrogen passes through the largely unchanged and makes up a major portion of resulting gas. Now coming to our next slide about carbon monoxide produced, moving on, we estimate the volume of carbon monoxide produced. So for each cubic meter of oxygen, 2 cubic meter of carbon monoxide are generated based on blast furnace reduction reaction. So multiply oxygen volume by 2, that is what we have earlier, we got 2025 multiplied by 2 is equal to 4050 meter cube per minute, and this is 4050 meter cube per minute carbon monoxide produced. So this step is key for estimating Bosch gas composition. Now coming to the total Bosch gas volume. Now sum the volume of nitrogen. First component is nitrogen, carbon monoxide to get the total Bosch gas volume. And hydrogen we have neglected here, that is 5475 and 4050. So this gives us 9525 meter cube per minute is the Bosch gas. Now, so this is the simplified Bosch gas volume. Later hydrogen and minor gases could be added for more accuracy, but this base method is operationally robust. So a shortcut formula and a practical example also can be established. Finally, see how these steps compress into neat formula, that is Bosch gas volume is equal to blast volume multiplied by 1 plus oxygen percentage as decimal, that is plugging in our values. So 7500 multiplied by 1 plus 0.27, that gives you 7500 multiplied by 1.27, that gives 9525 meter cube per minute, and matching our earlier result. So this shortcut is useful for rapid calculation and operational checks. So finally we can say that this is whatever the hot blast is going, is to be multiplied by 1 plus the available total availability of oxygen, that is suppose 26%, 25%, or 24%. So 24 divided by 100, that will give you 0.24. So 1.24 multiplied by hot blast volume will give you your Bosch gas volume. Similarly, if it is suppose 26% oxygen, then 1.26 multiplied by your hot blast, that is whatever hot blast is there, you multiply, we will get our Bosch gas volume. So this is a way how to mm, uh, remember, aid in memory, how much gas has gone up by enriching oxygen or enriching even coal injection. So this gives a feedback to operator to navigate properly, so that timely action can be taken to execute the day-to-day operation of the furnace.